This webcast continues the discussion of the lab activity for energy stored in a spring, and I'm going to resume at step 8, which tells us to create a graph of the applied force versus the displacement of the end of the spring. Okay, so in order to create a graph, I need to put the data from Table 1 into Microsoft Excel. And so I'm going to open up Excel. Let me just get a new workbook here. Okay. We have a constant, which is the spring constant, K. I chose 400, and the units for that are newtons per meter. Okay, it would be a good idea to put this block of constants at the top of your spreadsheet so that you can remember what constants you used. Okay, but then I'm going to put the information that I had in Table 1. Let me find Table 1 here. So it's going to look just like this. Okay, the first column is going to show the displacement of the end of the spring. That's measured in meters. That's awfully wide, and so I'm going to come up here and wrap the text. And I still see the displacement is kind of split on two lines, so I just shifted my column over to make it a little wider. Then I need the applied force, which is in newtons. I'm going to wrap that. And then I'm going to have the elastic potential energy stored in the spring. That's measured in joules. Okay, so now that I have these columns set up, I'm going to type in all of my data from Table 1. Okay, I've typed in my data, and it is asking me to make a graph of the applied force versus the displacement of the end of the spring. That means that I want the applied force on my y-axis and the displacement on the x-axis. These columns are lined up nicely to do that. So I'm just going to highlight the values in this table, and I'm going to go up and insert a scatter plot. Okay, so this might look a little strange because since my two axes are crossing in the center of this graph, right now I have this the values on this vertical axis in the middle of my graph. Just to make it more readable, I'm going to do a right mouse click on one of these numbers, and I'm going to tell it that I want to format the axis. And then down toward the bottom here, there's a drop down for labels. I'll open that, and I can tell it where I want it to put the position of those labels. The default is that it puts the axis labels right next to the axis, but if I choose low, let's see if I can get up there. If I choose low, it will move them all the way to the left. And that just makes it more legible. I can read it better. I could do the same thing here for the horizontal values. I'm going to do a right mouse click on one of those, go to Format Axis. I'm going to go down here to Labels, open that up, and tell it to put them in the low position. Okay, now I have a graph that's easy for me to read. Let me add some axis titles. Okay, so on my x-axis, I have the displacement of the end of the spring measured in meters, and on the vertical axis, I have the applied force measured in newtons. Okay, and then the title should be dependent versus independent. So applied force versus displacement of the end of the spring. Okay, so this is a nice graph. I could come and copy this and then just paste it in to at step 8. Here is figure 1, where it wants me to put this graph. I'm just going to paste it in there. My mouse is not working very well. There we go. Okay. So then it says, based on the shape of the graph, what type of relationship exists between the applied force and the displacement of the spring? Well, I'm sure that you can also tell that the shape of this graph is linear. So I'm just going to say this. The graph of applied force versus the displacement of the end of the spring is linear. Therefore, the applied force is proportional to the displacement of the end of the spring. Okay, so that would be a very nice answer to that question. Because the graph is linear, we have a situation where applied force is proportional to the end of the spring. At step 10, it says give the value of the slope, including the units, and then explain the meaning of the slope. So every one of these points is on the line, right? And so I'm just going to choose 2 values from my table and use those to calculate the slope. So the slope, and I'm going to show the calculation, that's very important. Let's see here. So I'm going to say 87.9, or oh no, I'm sorry, negative 265 minus 400, these are just the 2 points I'm choosing, over negative 0.663 and 1. This was newtons, and this is meters. And let's see what we get here. So negative 265 minus 400 is negative 665, and I'm going to divide by negative 0.663 minus 1. And I get 399.880. And the units here would be newtons per meter. So as I read this graph, going from left to right, the displacement of the end of the spring is increasing. And the slope is telling me, let's see, I didn't mean to do that. Let's see. So for every additional 1 meter that the end of the spring is displaced, right? I'm trying to explain what happens to the dependent variable for a 1 unit change in the independent variable. My independent variable, the displacement of the end of spring, was measured in meters. So for a 1 meter change of the displacement of the end of the spring, the applied force, and I can tell that as the displacement gets larger, the applied force had to get larger as well. So the applied force increases by 399.88 newtons. Okay. What is the common name given to this slope? The slope of the applied force versus displacement of the end of the spring graph is known as the spring constant, which is represented by the symbol K. Okay, and so then it says let's write a physics equation that explains the relationship here between the applied force and the displacement of the end of the spring. So for applied force, and that is my dependent variable, I'm going to call that F with an A subscript. And the independent variable here is the displacement of the end of the spring. And for that, I'm going to use the symbol for displacement, which is delta x. And so my dependent variable equals the slope with its units multiplied by the independent variable. Okay, it says ignore the y-intercept. Actually, I think the y-intercept is 0, but we're ignoring the y-intercept. Only the slope is very important to us here. So the applied force is a force that's applied by an external object. For example, us. We were the ones applying that force today. That causes the deformation of the spring. So that could be described as the applied force on the spring by the person. How would the spring force, that's the force that the spring is exerting on the person, compare to the applied force? So the spring force is a Newton's third law pair of the applied force. Right? They are the same type of force. They have the same amount. The spring force has the same magnitude as the applied force, but it acts in the opposite direction. Okay. So then, can we write a physics equation to describe the relationship between the spring, I'm trying to select a highlighter and that's not working. Let's see here. Between the spring force and the displacement of the end of the spring. So I want an equation that has spring force instead of applied force. I'm going to have the same slope. And I'm going to have the same independent variable. But the spring force, see, it has the same amount, that's why I need the same slope, but it's in the opposite direction. So I need to put this negative sign there. The spring force acts in the opposite direction as the applied force. If you recall, this corresponds to the slides that we saw when we talked about spring force, and we talked about how the difference between the force required to stretch the spring and the resulting spring force. The spring force equals negative k delta x, but the applied force just equals k delta x. It doesn't have a negative sign. The negative sign means that the spring force acts in the opposite direction of the applied force. Okay, I'm going to stop this webcast here and continue to the next one to finish this lab.